Hello, everybody. For our lesson for physics, we're going to cover spring mass systems and pressure volume work. What we're looking at is essentially a bunch of forms of energy that are changing from one to another, and this parallels the lesson that we already just covered in the classroom. So what we have here are our spring mass systems. For example, a surface where a spring is fixed at one end, and then there is a mass that is connected to the other end of our spring. In our system, the mass is 5 kilograms, and this is the part that can cause our spring to stretch out and eventually reach a new equilibrium position. Ln, in this case, that is the length, the natural length that the spring is normally at without the mass. And after being allowed to find a new resting position, that displacement was 7 meters. For our example, we're assuming that acceleration of gravity, g equals 10 meters per second squared. Determine the spring constants. Well, that's pretty easy for us to do. We're going to make the conclusion that at this new resting position, the restoring force F sub s, or the spring force, is trying to pull the spring back to its normal natural length, but the force of gravity of the mass is pulling down, keeping the string stretched, and these two forces cancel out, which means they have to equal each other. Because F net, or the net force along this axis, equals 0, we have the mass times the acceleration, with the acceleration equaling 0 as well. So in order for, F net equals mass times acceleration. The acceleration is 0, so F net has to be 0, which means that the restoring force minus the force of gravity equals 0. Thus, the gravitational force, Fg, and the restoring force, Fs, equal each other. The force of gravity is mass times acceleration of gravity, or mg, and then the spring force is our spring constant times our displacement, delta x. We already have 3 of these parameters, so our spring constant k is mg divided by delta x, or 5 kilograms times 10 meters per second squared, divided by our displacement of 7 meters. And that comes out to 50/7, or 50 over 7 kilograms per seconds squared. We just found the spring constant for that spring. Now, let's assume that we have the same exact spring, but we put a different mass onto the end of that spring. We already determined that the spring constant is 50 divided by 7 kilograms per second squared. G is 10 meters per second squared, as we are assuming. We also have our initial velocity vi of 0 meters per second. What we're going to be able to find now is a bunch of valuable parameters just from the few that we already have. Let's say that once this mass is allowed to drop and our spring stretches, it's going to move back and forth for a little bit, but there is a point where these two forces once again cancel. The restoring force, the spring force, and the gravitational force at this point, our change in displacement, delta x, is also going to be our change in height, delta h. Now let's start using these parameters. First, let's determine our displacement, delta x. Well, that'll be mg over k, mass times gravitational acceleration over our spring constants. The mass that we're given is 16 kilograms. We're told that g is 10 meters per second squared, and we already determined in the prior example that k is 50 over 7 kilograms per second squared. This gives us a displacement of 22.4 meters. Now, something that we can calculate is the change in potential energy of gravitation, or gravitational potential energy, delta UG. Its formula is mg delta h, mass times gravitational acceleration times change in height. Now, our displacement of our spring happens to equal the change in height of our mass. But we'll need to make account of one thing. The change in height in this problem is negative. So instead of 22.4 for h, we'll use negative 22.4. 16 kilograms times 10 meters per second squared times negative 22.4 meters gets us delta UG equaling negative 3,584 joules of energy, or in essence what a kilogram meter squared per second squared is. That's a joule. The negative means, unlike with a vector, where negative and positive means some direction on a cardinal plane, for energy, a scalar, the negative just means this is leaving our system, or this is potential energy that the mass originally had, but because it dropped in height, it lost gravitational potential energy. That energy went to other parts of our system. Delta US, or the change in spring potential energy, its formula is 1/2 times the spring constant k times the change in parentheses our final displacement squared minus our initial displacement squared. Emphasis is squared on the inside, not squared on the outside. We're not squaring the difference, we're taking the difference of squares. Well, our final displacement is basically that 22.4 meters. Our initial displacement, by that I mean displacement from the natural position of the spring. Well, if it's already at its natural position, then its initial displacement is 0 meters. So 1/2 times 50 over 7 kilograms per second squared times the quantity of 22.4 meters squared minus 0 meters squared. This gets us positive 1,792 joules of energy. Therefore, of the 3,584 joules that left the mass, half of that went into the spring to extend it further past its natural position. As far as kinetic energy goes, the change in kinetic energy, delta KE, we are going to take the difference of our potential energy of gravitation and our spring potential energy, but we're going to flip the signs. Or what you could do is put this in absolute value signs. Basically, of the total amount of energy that could have gone to kinetic energy because it left the mass, how much of it did not go to kinetic energy? So that's why I changed 3,584 to a positive number and 1,792 to a negative number. This tells us of the amount of energy that left gravitational potential energy. this is how much went to the change in kinetic energy of our object as it was falling down and first reached its resting position and then kept going and springing back and forth until it reached this position. But the first time it reached this position, this is the change in kinetic energy. That would be 1,792 joules. So half the energy that was lost by gravitational potential energy went to the spring potential energy, and the other half went to the kinetic energy of our mass. Delta KE equals 1/2 times the mass, m, times the quantity, VF, V velocity final squared, minus VI, or velocity initial squared. Again, this is a difference of squares, not a squared difference. Rearranging our equation to solve for VF, we have the square root of 2 times the change in kinetic energy over the mass plus VI squared. So the fraction delta KE times 2 over m. Added to that fraction is VI squared. All of that is under 1 square root. Therefore, we have the square root of 1,792 joules times 2 over 16 kilograms plus 0 meters per second squared. This gets us the square roots of meters squared per second squared, or meters over seconds. The exact answer is 4 times the square root of 14 meters per second, which is about 15 meters per second. Next thing we can calculate is delta t, which is roughly the change in velocity equals the change in displacement over the change in time. So delta t is delta x over delta v, or 22.4 meters divided by the quantity 4 square root of 14 meters per second minus 0 meters per second, or the initial velocity. This gets us to a change in time of 1.5 seconds. Our last parameter that we can calculate from this information that we had from the start is power. Power is work divided by time, which according to the work energy theorem, work happens to be equal to the change in kinetic energy. So we can set power equal to the change in kinetic energy, delta KE over delta T, which would be 1,792 joules over 1.5 seconds, which gets us to 1,194.66 repeats watts, capital W for watts, which is the same thing as a joule per second, joule of energy per second in time. So from just 1, 2, 3, 4 bits of information and our drawing that allowed us to assume forces, we were able to calculate 1, 2, 3, 4, 5, 6, 7 parameters. Technically 8 because we were able to implicitly calculate work from kinetic energy. But we calculated 7 things from just a simple spring mass system. Next thing and the last thing is the work of thermal expansion, WTE, or work of thermal compression, WTC. It doesn't matter which one we're doing. Basically, is our volume expanding or is our volume compressing? Well, what that is the following. We're going to have the same exact formula for both. Our formula for thermal expansion or compression is work, W, equals negative P delta V. P is pressure in pascals, or PA, capital PA. Change in volume is going to be cubic meters, or m cubed. Now, if your container is a cylinder, volume equals pi r squared h, with the radius usually being a constant. Therefore, change in volume, delta V, is pi r squared delta h. For the volume of a cube, volume equals length times width times height. So the change in volume is the final length, width, height minus the initial length, width, height. LWH final minus LWH initial. Let's say we have a cylinder or a piston with a pressure of 10 pascals, a radius of 2 meters, and an initial height of 5 meters. After its initial position, a transition over 3 seconds to the final position, we have pressure still 10 pascals, the radius still 2 meters, but the height increased by 10 meters. Well, let's look at this. We have an expansion, so we're going to use WTE. If the reverse happened, where we had a large height that became a smaller height, then we would just use TC. Anyways, our work is negative P delta V, which for a cylinder is negative pressure times pi times r squared times the difference in height, h final minus h initial. Always remember that negative sign for this equation. That's a common error. So negative 10 pascals times pi times 2 meters squared for r squared times the difference of 10 meters minus 5 meters. Another common error, it's always the final height minus the initial height. I've seen some students always put the larger number first, but sometimes the height actually decreases over time, not increases. You have two options. You can either leave pi as a symbol, basically just don't plug it into your calculator, at which point we get work equaling negative 200 times pi joules. If you do plug in pi into your equation, then what you're going to get is work equaling negative 628 joules. So either include pi in your calculation or just leave it out when you calculate something, but then plug it back in to your final answer. Third common error is just forgetting to include pi. If you left it out of your calculator, include it in your answer. If you include it in your calculator, then do not write it again. Now, power is still work divided by time. We calculate our work equaling negative 200 pi joules divided by our transition of 3 seconds. That gets us negative 66.6 pi watts. If instead you use the answer where pi is not kept as a symbol, but it's evaluated into our answer, then what we have is negative 628 joules divided by 3 seconds, equaling negative 209 watts. If you are in my class, then for your worksheets for your tests, it's okay to leave pi in your answer or include pi in the actual evaluation. Just be sure to write it in your answer if you did not use it in your evaluation. And if you did use it in your evaluation, then do not include it written in your final answer. As for why we have joules for work, it's because a pascal times a cubic meter equals a joule of energy. In any case, that concludes our lesson video. For our lesson, future lesson, past lesson, or just random video on YouTube for our spring mass systems and work of thermal expansion and thermal compression. The only difference for thermal compression is you'll use the exact same equation, W equals negative P delta V. It's just that you'll end up with work and power equaling a positive number instead. But keep it negative P delta V before you plug in your numbers. As always, you are welcome to just enjoy this video, or you can comment, like, and subscribe to see the rainbow buttons show up if they still do that. But whatever the case, glad to have you all for class or outside of class, whether actually in class or in just some video. Glad to have you all, and peace.